I'm representing, as you can see, a pretty large virtual team that's spread across current employees, past interns, and people in different universities that we work with. And we're working on a project called Spec, and I'm going to try to take you into the future, because what we'd like to do is be able to provide the tools to work on large systems and still know a great deal about how correct they are. And to us, the main reason that doesn't happen today is because whatever programming language you have, you're given a set of tools, and today you've heard a lot about D-Link and adding new tools to that, the languages you use. But what all of those languages leave out is the ability for you to record the design decisions that are often the most important part of the program. And if you've ever picked up a program that you'd written in the past or that someone else had written, you know the hardest part is not understanding what the program does, but understanding why it works and what were the decisions that the programmer was intending when they wrote the code, so that you can understand those decisions. And then we want those design decisions to be recorded in a way so that automatic tools can be used to amplify, to enforce the decisions that were made, and to guarantee their consistency over time. So let me, lack of time, let's just jump right to the demo. So what I'd like to show you is a day in the life of a Spec programmer. And probably as I do this, you will see lots of the errors before the system is able to catch them. But the point is perhaps not for programmers as sophisticated as yourselves, but whether or not that sort of thinking can be brought to bear for the general programmer. So I have here a very simple class called Chunker, and it's intended to be an extremely stupid tokenizer. So you give it a string and you give it a size. You can see the constructor here. And then every time you call this method nextChunk, it should return to you the next fixed length substring of the original string. And what you're seeing is our integration into Visual Studio, and so we already have a warning from the Spec compiler that's above and beyond the kind of warning you would get from the current C# compiler, which is that you're dereferencing this instance field, src, but since it's of type string, a very possible value for that is to be null, and at runtime, if the value is null, you'll get an exception thrown at that point. And it's very common for programmers to write their code, and they intend it not to be used on values that are of the value null, but there's no way for them to sort of record that now. And what we say is, well, the most common, that's probably the most common design decision. So we give a very lightweight notation for it, namely the exclamation mark means that this field is of type string, but excluding the value null. The value null can never be a valid value to stick into that field. And I don't know if you can see the squigglies from back there, but you immediately get another warning here, which says now that you're taking an arbitrary string from a client and you're trying to stick it into this field that is supposed to never have the value null. And so the way to fix that is to advertise to the client that part of your API now is such that it is not valid to call this constructor and pass in the value null for the string. That's just an incorrect program. And now the Spec compiler will refuse to compile a program that calls this constructor without guaranteeing that the value is not null. Let's see. And so while we're thinking about it, there's other things. Probably nextChunk is meant to give back a non-null string. Let's see. So what do I want to do now? Okay. So the errors we've been seeing so far come from a part of the compiler that is just uses a static data flow analysis. But for some deeper errors, you actually need more help. And so we've hooked up the compiler to a theorem prover under the covers. And let's see. What else do we want to say? Oh, we can say that the result of the method, its length is equal to chunk size. And now we get an error because chunk size is a private field, but we're using it as part of the public specification of the API for this method. And so we'd like to make this public also, but We certainly don't want clients modifying it, so we can make it read-only. And now we get another complaint, and that's a much deeper complaint. Yes?
How do you deal with the fact that when chunker is first allocated, source will be known? And from the constructor, you might say, call it the type of method or something of that nature.
Yeah, good point. Okay. Let's see here. Right. So the question was, how do you deal with the fact that, how do you make this type safe? So let me get to that in just a minute, as soon as I finish the demo. Right. So we had to provide, right. So if this is, to make sure this is type safe, namely that that at any point that you could observe the value of that field, that it's a non-null value, we have to make sure that the constructor behaves correctly. And there's actually a couple of different ways to solve that problem. I'll show you one in just a second. Yeah? Okay. So what you're seeing now is a much deeper error in the sense that I don't know of any static data flow analysis that's going to give you this error message. And actually, this one comes from the theorem prover that I turned on when I went to the project properties. And it's complaining about the fact that the first parameter to substring must be non-negative. And as you can see from the comment on the field n, that's intended to be true. N is initialized to 0 in the constructor. It is only incremented in this method. And so we would hope that it's always non-negative. But there's no way, there's no enforcement of that. Yes?
Couldn't you use an unsigned int?
Yeah, that's another possibility. I'm sorry, the question was, could I use an unsigned int? And of course, yes, I could. But another possibility is, maybe for some other reason I want it to be an integer, and I'd like to have some enforcement that n is always non-negative. And that's not a property of that particular method. It's a property of the entire class. For this class to be in a good state, n should be a non-negative integer. And you describe what the good states are for an object by using class invariance. And so now we still have a complaint on that line. And now, of course, it's complaining about the second argument. It's a substring. You know, of course, this demo is carefully constructed so that there's 3 preconditions on substring, and we're going to violate every single one of them. So now substring is, chunk size is not known to be non-zero. And now that I think about it, the only thing I'm getting from that precondition is that chunk size should be non-negative. But if I think about, well, do I want to say it should be, is it possible to have it equal to 0? Well, it's certainly possible to have it equal to 0, but that seems like a bad decision as I'm writing this class, because then every time I call next chunk, I'm not making any progress. I'm just getting back an empty string. So this is what I meant earlier by saying that we allow you to record arbitrary design decisions, and then we give tool support to enforce those. So this says that the value chunk size will always be positive, and it will be positive even across subtypes if there were to be any subtypes. And before I look at the last violation of the call to substring, the precondition violation, notice that now it tells me that even though the invariant about n was satisfied by the constructor, the assigning of an arbitrary integer to chunk size might violate that invariant, and certainly at the end of a constructor, the invariant should hold. And again, just as I did for adding to the API for the first parameter, I can tell clients that they should not call chunk size with without a positive value for the second parameter. Okay, sorry. So one last precondition violation is that the sum of those two values better be no longer than the string. And there's no way to statically do this. There's no way to guarantee that I won't violate that condition. If I think about it, I'm taking the string and I'm marching through it, and at some point, indeed, the place I start at plus the chunk size might run over the length of the string. But you can take any precondition failure and you can always turn it into a runtime test. And now I'm guaranteed not to violate that precondition, right? Because I'm testing for it at runtime to make sure I'm not going to violate it. And now that makes me think, well, what am I going to do in the case that I am going over the end? And again, there's several options here, but I can just decide to ask for the remaining characters. You know, I could think maybe padding it out to always give back something of length chunk size, but instead I can just call substring and ask for the rest of the characters. And now it's saying that there's a problem with the start index possibly being over the end of the string. And again, I only recorded half of that comment in the invariant, and the other one is that n should always be a number between 0 and the length of the string. And now I'm being told that, and now this is a slightly more long story to tell you, but it's about when do these invariants hold. The easy story that you would like to be true is that methods are atomic, that it's sufficient to validate an invariant at the end of the constructor, and then every public method can assume that the invariant holds at the beginning of the method. It may mess with the fields and violate the invariant during the method, but before it returns, it will revalidate the invariant. So the client will never see that the invariant doesn't hold. And if methods truly were atomic, that would be the end of the story. But as you probably recognize from a lot of programs you've written yourself, that's almost never the case. It's very frequently the case that you make some method call, and instead of being just a nice safe downward call to a library, it actually calls out to an object, which calls another one, which calls another one, which ends up re-entering this class either in the same method or another method. And now that atomicity has been broken, and the fact that your object is in an inconsistent state is visible. And so you can't have it be the entire method, and it's often infeasible to have every statement keep the invariant true, because if you have an invariant over multiple fields, it may take some manipulation before they're true. And so we just leave it up to the programmer to tell us exactly what the span of time is during which the invariant's not going to hold. And it's like a lock statement. It says within this block the invariant does not need to hold, but at the end of the curly brace the invariant better hold again. And in between you are prevented from making any calls that could result in a reentrant call. And of course I'm being told now that the object invariant might not hold there because I'm incrementing n by that full chunk size, even though I have this nice branch telling me whether I'm going to go over the end. And so that's easy to fix just by, I shouldn't be incrementing it by chunk size each time, but by the length of the string that I'm returning. And now, one last warning, which is that next chunk is advertising to clients that it's always returning something which is of length chunk size, and we just talked about the fact that that may not be the case. And so the most I can say here is that the result length is at least the chunk size. And that's it. Now there's no more squigglies. So sometimes you do this demo and people say, that's horrible. Why would I ever want this? This is like the worst possible programming environment. I wanted to write a simple class and look at the pain you put me through. Right? But what we'd like to point out is now, where are all the test cases I have to write? Where are the unit tests? Where are the corner cases? All the corner cases are gone because the theorem prover explored those for us as we were writing the code, instead of having to think ourselves of all the possible, well, what if this is null? What if I'm at the end of the string? What about an off by one error? All of that has been taken care of for you because we're using the tools to provide enough rigor to check those out for us. Yeah?
The local variable s is declared as a nullable string?
Ah, good point. Yes. That's right. So we're allowed that because we do enough. I'm sorry. So the question was, s is defined as a local variable of type string, not string bang. But we do local inference inside of methods. So for any local, we're going to track in the control flow if it's null or not null. So we know inside of, we know from the contract of substring that substring gives us back a non-null string, and that's assigned to s. So yeah, that's a good question. Nobody asked that before. Where did we get these preconditions? Right, and we have a tool that we use to heuristically mine the BCL, looking for patterns of the form, if such and such holds, throw an exception on a parameter, and we turn those into preconditions. So we call those out-of-band specifications, and when you use Spec Sharp, you actually can create your own out-of-band specifications and apply them to third-party libraries if you don't have the ability to annotate those libraries directly. And then we've gone in by hand and added certain post-conditions that we are, feel are valid. Yeah?
Your post condition is incorrect. You should say relative, not
Yes, that's a good point. No, I'm sorry. It's here, that the return type is string bang. So that's where we get the post-condition that it returns. Yeah, equivalently, you could say result is not null. And in fact, yeah.
I was reading
Right. So the question was that ESC Java was a similar system and had problems with object invariance sort of spreading to become, what, too much of the program, I guess you're saying?
The paper said that it didn't prove feasible in large projects.
Right. So one of the authors on the first slide, Rustin Leno, on our project, actually was one of the inventors of ESC Java. And in large part, Spec Sharp is the evolution of that technology to fix a lot of those problems that ESC Java had. So ESC Java is a very similar kind of system for Java and has had problems in a couple of ways. One was that invariants were not treated soundly there. So they did not have an expose construct, and they tried to go with that very simple idea about invariants being assumed to hold at the beginning of a method and only needing to be asserted at the end of a method, which is unsound. So we make the sound choice. In other words, if you do not get a violation from our checker, you're guaranteed that those invariants can never be violated. Whereas ESC Java was a checker. If it gave you some errors, they might be errors, but if it told you your program had no errors, maybe it didn't or maybe it did. And the other thing we do is, what I don't have time to get into here, is the way we handle object invariance creates a difference between the internal view of an invariant and the external view. From the external client's point of view, they never see the details of what is in the invariant. They only have to be aware of whether the invariant holds or not. And that proves to be much more tractable in our system, I think. Okay. So right. So what we're trying to do is lead languages like C# into the future where we think there will be contracts everywhere, because these are the kinds of descriptions of code that are really needed in order to use code wisely, to be able to use it without getting errors. And all we're trying to do is push the boundary of the kind of checking you get along from the current type checking to give you first runtime checks, and then, as you saw in the demo, actual static verification. Yeah.
You adorned the BCL with pre and post conditions. You didn't actually update the BCL file.
No. So the BCL has, we never touched the binaries. What we have I'm sorry, the question was about how did we get the contracts onto the BCL. So we have a mechanism for having out-of-band contracts. In other words, you write a shadow assembly that contains just the specifications, and then our compiler will fold those shadow assemblies and the actual assemblies together for use inside our compiler. And inside for us, it will look as if the original assembly did have those annotations. So the verification you get is modulo how trustworthy those third-party annotations are. Yes?
Is there some overlap between what you're doing and FXCOP?
The question was, is there overlap between what we're doing and FXCOP? There's overlap in the sense that we are checking assemblies against design rules. The difference is that FXCOP checks for, effectively checks for a static set of predefined rules. They say, here are the rules, and if your code violates it, we're going to check for that. And what I'm showing you here is a system where you define what those rules are. So in that demo, we defined what the correct usage was of the chunker class. And now if you write any client code that used that class, Spec Sharp would analyze your code and make sure that you had no errors relative to the design rules that we imposed as the specification of chunker. We also saw it in the chunker demo. Most of that demo is about making sure that internally the chunker class itself was correct as a client of the BCL. In other words, mostly of the call of string.substring. Okay, so I'm certainly not going to have time to go into anywhere near these. Let me just talk about the non-null types a little bit more because there was a question about that. As you saw, right, we introduced non-null types, so the bang means that something is definitely not null. We give you escape hatches so you can cast things quite conveniently to be non-null types, and you get a runtime check for that. We do a data flow analysis, as I said, so that you don't have to do complicated programming constructs. We'll know whether or not something that is a possibly null type actually is non-null based on the control flow. And then one of the questions was, what do we do about type safety with base call in the constructors? So here's the example. For that, class C has a field X, which is, it would like to think of as being non-null. So that means we can write a method M in class C that dereferences X without having to worry about the fact that X might be null. And it seems everything should be okay because we take a non-null value of type T at the constructor and we assign it into the field. So it seems like there should be no problem with that at all. And the question is it type safe? Is it possible to ever view this field X before it receives that value? And as someone pointed out, there's definitely a problem because the base call in C# happens before the body of the constructor runs. And if the base call calls a abstract method M, which gets dynamically dispatched down here, that will be evaluated before this assignment is able to be executed and storing a safe non-null value into the field X. So there's several ways to solve this problem. One way that Spec Sharp allows is that we give you freedom to put your base call anywhere you want. We don't restrict it to be before the body of the constructor. So this is legal Spec Sharp syntax. This is a departure from C# in that we allow the base call to happen arbitrarily. It turns out in all the examples we've run, we always end up putting it at the end of the constructor. So it seems like if you were going to design a language fresh, I would highly recommend putting the base call at the end of the constructor rather than the beginning of the constructor. But we also have some other techniques that can solve this. Yes?
This leads to a problem where you could potentially violate an invariant of B by calling a method of B before calling the base constructor, or do you check for that automatically?
Okay, the question was, could we violate an invariant of the base class by trying to call a method on it before the base call has been made, in which case it's unlikely that the base class will be in a valid state. Yeah, we absolutely check for that. So if you were trying to call some method on the base class before the base class constructor was called, that's exactly where we track the state of an object as to whether its invariant holds or not. So the precondition on those base methods would be that the invariant should hold, and you wouldn't know that yet because you wouldn't have finished calling the base constructor.
Doesn't the verify disallow that kind of code? I thought it required the base constructor first.
Okay, the question was, won't the verifier reject this kind of code? No, actually, the CLR does not require that the base call happen before the body of the constructor. It's just a C# restriction. So the IL that gets generated from this is fully verifiable. There's actually no problem with calling the base constructor later on. Okay, so I'm supposed to wrap up there, so let me just say that there's lots of other non-null issues. Oops, where do we go? Static fields, static non-null fields are a problem. Arrays of non-null elements are a problem. Similarly, closely similar to arrays of non-null elements, generics over non-null elements are problems. We have some solutions for some of those. Some of those require runtime support that make it difficult. We actually have a C# compatibility mode where all of the Spec Sharp features can be expressed just in terms of things that look like comments to the C# compiler, but that our compiler will pick up. So you don't even have to use the Spec Sharp language service. You can continue to use C# and only add these things in comments so that you can use our tool to check it, but not actually to do the compilation. Even the base calls can be done that way later in the constructor. This is the full story about object invariance, but I definitely don't have time for that. Let me just jump to the end here and then I'll take questions. Okay, I just wanted to get this on. So this is our URL. There's a public download. It's freely available. Everything I showed you today will work right out of the box when you download Spec Sharp. We're working very hard to extend it in many ways, and I'll take any more questions.
When do you expect this to be released or eventually go to production?
So the question was, when do we expect this to not be released as a research download from the MSR site, but to make its way into real products? I don't know. We tried to design it. One of the reasons I was stressing the non-null type system is that we've tried to design Spec Sharp in a way so that there are features you could peel off and integrate without having to buy the whole story. So I don't know. Yeah.
Second thing is, I have a similar tool called Static that I'm trying to deliver in a few months. It doesn't go as far as what you do, but it does perform symbolic execution. And I was looking at some of the work you do. I noticed that what some differences between what you do and what I do is that I can handle more dynamic behaviors like closures and iterators and virtual functions. I don't know, you probably handle those as well. Loops, I noticed that with loops, you pull away some of the values from, you don't necessarily, you don't create recurrence relationships. You don't create the recurrence relations on the values, on the variables that change, which would allow you to actually reason exactly about how the variables change within.
Okay. So the question was that you have a tool named Ecstatic, and it's got some different features. I'm not sure. So if we're talking about programming features, Spec Sharp is a full superset of C Sharp. So it has all the features of C Sharp. But if I understand your question specifically about the verification of loops, you have used recurrence relations, which is can be seen as a form of abstract interpretation to try to more precisely model the effect of the loop. And I didn't have time to go into that, but we have an entire abstract interpretation framework inside of the system, and we do some loop invariant inference to try to get a more precise picture of what's going on in the loops. Okay. All right. Thanks.
Are the capabilities of the theorem prover accessible to other compilers?
Yeah. So I ran out of time there, but one thing I wanted to say was that we actually have have decoupled Spec Sharp from the use of the theorem prover by instituting an extremely explicit boundary there. Namely, we've created an entire intermediate language called Boogie PL. Spec Sharp is translated to Boogie PL. Boogie PL is then processed, and that's what communicates to the theorem prover. And we've had very good success with. I mean, it's worked out very well to create that boundary. There are other groups in the world that are providing backends from Boogie PL to their verifiers, and there's also other systems that are thinking about generating Boogie PL from their source language. So it's and that's completely accessible from the download, although the documentation is pretty much non-existent. And with that, I'm out of time, so I'm happy to talk to you more out there as we get pizza and beer. And
You for compatibility with C Sharp, you put all this stuff in the comments. Why not in the attributes?
Okay, this will be the very last question after the last question. It says, why didn't we put everything in attributes? There's several things you lose out when you try to stuff everything into attributes. A lot of it is the restriction of the language you can use in custom attributes. So you have to encode things in strings. But yeah, it would be possible to encode a lot of things in attributes.
No, I mean, if at least in compatibility mode.
Yeah, I understand. So in the compatibility mode, you could do it all in attributes, but we just chose this comment convention. Makes it very easy to move back and forth between Spec Sharp and C Sharp. So we can talk further afterwards, but great. Thank you.
Thanks very much.